I'd like to introduce the first speaker of the day, Professor Regina Barzilay. She's a professor of the Department of Electrical Engineering and Computer Science and a member of Computer Science and Artificial Laboratory at MIT. Her research interests are in natural language processing. Currently, she's focused on bringing the power of machine learning to oncology. She works together with physicians and her students to devise deep learning models that utilize imaging, free text, and structured data to identify trends that affect early diagnosis, treatment, and disease prevention. She received her MS and BS from Ben-Gurion University at Negev and her PhD in computer science from Columbia University. She also spent a year at postdoc at Cornell University. Professor Barzilay is a recipient of various awards, including the NSF Career Award, the MIT Technology Review TR35 Award, amongst many others. She also received a MacArthur Fellowship, an ACL Fellowship, and a Fellowship of the Association for the Advancement of Artificial Intelligence. Now, before I bring her up here, I do want to say a fun fact about Regina. She has a hobby of deciphering ancient languages with machine learning, so I thought that was really interesting. Everyone, please help me welcome Professor Regina Barzilay to the stage.
Thank you so much. Thank you. I'm really honored to be here, and I honestly don't remember when was the last time I spoke to such a huge audience. I can't really see your faces because the light is in my eyes, but if something is wrong, just wave me. Okay, so what I want to talk to you about is about power and limitation of machine learning for clinical applications. So clinical applications are particularly interesting because this is the case that the data is collected in masses in every single hospital system, and we really want to utilize them. So my traditional background, as we heard from Kate, is in machine learning and natural language processing. You know, 5 years ago, exactly 5 years ago, I was diagnosed with breast cancer. I went through the treatment in Massachusetts General Hospital, and then I realized that all this amazing data that is collected about patients is actually not used at all to improve treatment. So since then, in addition to my usual MIT duties, I decided to change it, and I will share with you some of my observation. I work in two areas, using clinical data that I will show you some examples, and using deep learning for chemistry and drug discovery. So the area of AI and medicine is actually a very funny one, and I will tell you why it is funny. Because if you open any newspaper, like try it on Google, you would see, you know, hundreds of different stories about AI in healthcare. However, if you go today to the hospitals, it's very unlikely that you're going to find any AI there. And in fact, there is this big survey that was conducted about how much AI is in the hospitals. And the result of the survey was only 5% of the healthcare system actually trying to utilize AI. And I think, you know, there is a definition, what does it mean to use AI? There is actually a great opportunity to use AI in care. Think about it. Whenever you're going to the hospital, the things that they do, they collect a lot of images and tests and so on. So for instance, you may have an X-ray of your chest or something else. Now you have a human who summarizes what they've seen on these X-rays, which is hundreds of thousands of pixels. They get summarized in a page. But this is not even what the doctor uses to decide your treatment. Then these stories are translated into a few categories, and then you get treatment. So if you're to think about Amazon or something like that, it would be as if, you know, we are divided all to 100 categories, and all of us are getting the same books for the same bucket. And then, of course, what happens is that once we did this abstraction, which is extremely coarse, correct, very coarse, the people who are very different, and here you can see 4 pathology slides of women which are in... There is something wrong here, okay, I cannot move. So what you can see here, you can see 4 pathology slides of women which are in the same bucket. 3 of these women were fine, 1 got metastatic recurrence. But we cannot say it because according to how we summarize them, they look exactly the same. And another fact that we, as patients or future patients, should be really concerned about comes from the American Society of Clinical Oncology, which says that today all the clinical decisions are based on 3% of the population that participated in clinical trial. So I'm sure that all of you are working with data in one way or another. Imagine to yourself you're throwing away 97% of your data. So the way, when I came back after treatment at MGH, I imagine we are going to be working, is taking all the raw information about the patient, all the data available, and making predictions. The same, again, as an Amazon analogy, where you are just going through the, taking all the information, whatever you bought, what pages you look at, and make recommendation. And in this case, we want to predict recurrence, to see whether the patient responds to treatment, identify a population at risk. And the first applications that we actually started doing was in imaging. And the reason we look at imaging, because this is a technology that is extremely mature. So the same way here you can see deep neural net, which try to identify, this dog, which is kind of non-trivial to identify. You see that this image is translated into a matrix of pixels. A number of nonlinear transformation is done, and you kind of adjust the wires in such a way that it makes correct prediction. Instead of identifying cats and dogs, we can do the same with mammograms. We can teach machine to read mammograms, and that's exactly what we've done. For the last 14 months, our deep learning model is used to read jointly with the radiologists the mammograms. And you can actually see here, MGH is Massachusetts General Hospital, which is very close from here. So what you can see here, this is a radiology room. This is my collaborator, Connie Lehman. The machine reads the image, she reads the summary and approves it. So this is where machine can help radiologists. But actually, what we can do is to move beyond just doing the tasks that humans can do. Because humans, have limited visual capacity. So what you see here is the breasts of two women. None of them have cancer at this point, at this image. However, one of these women developed cancer within 3 years, and another didn't. If you show these images to the radiologists, they would be unable to predict it. However, if you're thinking about machine, maybe you can train machine to do it. And now this is a really interesting point of how you can use AI in a different way. So for instance, how can you predict a risk, be it a risk of breast cancer, of Alzheimer, or whatever? You go and collect the factors that you, with your human mind, think correlate with an outcome. It can be family history, your age, your race, whatever. Okay, then you run statistical model, you get the number. So for those of you who are not familiar with the area under the curve, this is a measurement that is 0.5 when you're making a random guess. It's 1 when you are perfect. So you can see that the models today, which are not deep learning models, which are traditional statistical models, they have an accuracy really closer to the random end of the story. These models work well on the population level. They're not good enough at the individual level. So instead, what we've done, we gave the machine the images, and we told it, for this image, we know the woman developed cancer within 5 years. For this, we know they didn't. Of course, we looked at the past images, and we tried 2 types of model. One which was image only. Another one had some traditional risk factor, like your, for instance, genetic risk and so on. And what you can see here, that this model did way better than this blue model called Tyrer-Cuzick, which is used today clinically to actually put women on chemo prevention. And this is really surprising because the blue model was studied over almost 2 decades. There are lots and lots of papers written. You can see that just bringing the data and algorithm, you can already do so much better. Now, let me give you another view of what it means for those of you, again, who doesn't have a good feeling about AUC. If you are to take all the cancers that you have in the population and see how many of them fell into top 10% as predicted by the model. So our model in the top 10 high risk put 31% of the patients who had cancer. For the model which is currently used in clinical practice, it's only 18%. And similarly, the other model makes mistake in terms of who is low risk. But now I want to show you the slide that for me was really disturbing when we made this discovery. It is common in medical literature to stratify your results according to age and race. And I want to show you the result based on race. So what you see here, the deep learning model sustains the same performance across white women and African American women. What you see, the model which is currently in clinical practice is actually below random on the African American women. So now there is a lot of discussion of what AI is doing in terms of not being racist. My point is we have already so many legacy models that were not developed properly for certain subpopulation, and we are sometimes even not aware of what they are. So there are several immediate lessons out of it. One is that it's time to change the model. And the second one, that when we are training our AI models, we really need to make sure that we are using the correct data. In this case, we use really the outcomes, but if we are taking the models which have bias, which have been in medical systems, they actually can introduce extra bias. But luckily, deep learning model was doing quite well. So another area where, again, you can totally change the way clinical processing is done is analyzing text, because everything we know about patient is written in text. And what we've done, we built a system for Partners Institution, which contained Dana-Farber, MGH, and several other hospitals, a system which take information about all the breast cancer patients that went through the system in the last 30 years, and it extracts automatically all the information about the features of cancer. I mean, for those of you who don't know much about cancer, it's okay. It tells you, does it have lymph invasion, what type of cancer, and so on and so forth. And you can say, is it really important? I mean, from natural language processing perspective, it's actually really an easy task. And here you can see my collaborator, Dr. Kevin Hughes, who uses this system, on daily basis at MGH, both for clinical use and for research use. He's really a surgeon. He just doesn't want to wear a white coat. But the reason it is so important, I want to give you a fact that was really an eye-opener for me. In this country, you have to have cancer registry. So every patient that had cancer is recorded in this registry. This is done by hand today. When there is technology to do it better, we are wasting money, we're introducing mistake, we are delaying it, and there is really no good reason. So this system is trying to automate it. And the funny part is that when I talked to the head of Massachusetts Cancer Registry and proposed for this system for free, she told me that they're doing well and there is no need. So it really shows to you that, that it takes a while. And also another question that people ask is how challenging it is to build such systems. And I would say absolutely with machine learning. Actually, the surgeon that I show you, Kevin Hughes, originally he hired a company which by hand was writing different ways to say that the patient have, lymph invasion or hyperplasia. This is his slide. It turns out that many people at MGH are kind of small Shakespeares, and they write in a very different language, and even the same disease you can call by many different names. So machine learning can absolutely robustly handle it. And you can see what it does to you, how it totally changes the game. Like, for instance, New England Journal of Medicine, which is the top medical journal, published an article about a condition which is called atypia. It's a precancerous condition. Millions of women in this country have it. Now, they published a paper on 674 cases. You can say why? Because a human had to go by hand through 10,000, and not a human, a medical doctor, through 10,000 cases to identify this subset. With one simple query, you can identify 6,000 cases at MGH alone. Another example, overtreatment. So there is a condition which is called high-risk lesion. If you got diagnosed with this condition when you do your mammogram and biopsy, all of the women who have it has to have a surgery. It has to be excised. Only 13% of them actually had cancer and needed the surgery. So again, using the data and simple machine learning, you can cut the number of unnecessary surgery by 30%. Okay, so at this point, I told you all these wonderful things that machine learning can do. And, and it became kind of a magic power. It works for everything. It can solve every single one of our problems. So the second 16 minutes of my talk, I am going to talk about when it doesn't solve the problems, that it is not a magic power, and we really need to be aware how carefully we should be using it. So let me start with this example. What do you see on the slide? A pig, correct? Somebody may say lunch, pig, whatever, but it's a pig. Okay, so here we have a pig. Again, we remember that the image is represented as pixels. So what we are going to be doing, we're going to take this pig, and it's absolutely correctly identified by any deep learning computer vision model as a pig. We are going to generate some noise and add it to the pig. And now this pig becomes an airliner. The same trained system takes this image and identifies it in a very different category. So of course the noise that was added to the image was not random, and it was engineered in a certain way to confuse the system. But you can see that with this kind of adversarial approaches, you can really confuse the models. And this is, let's hope it works. So this is something interesting that was constructed by students at MIT. So this is a turtle, correct? But if you can see, this bar, it's what neural network sees. So from every single angle, whenever you are moving this turtle, the neural model identifies it as rifle. And even if you put two of them, it's still a rifle, correct? So this is very interesting. You may be sitting here and saying, okay, there are these weirdos at MIT that are creating these funny things and make pig fly and other things, correct? But in reality, in our data, it never happens. Because our data, there is nobody malicious who actually going and spending time to create it. So let me show you something when there was no malicious intent, and it resulted in super funny story. How many of you, and I can sort of see it, how many of you know about Hathaway phenomenon? Like an actress Hathaway. Okay, we have one person. Okay, so this is like really a funny story. It turns out that for a long time, each time when Anne Hathaway was in the news, the stocks of Berkshire Hathaway went up. And a blogger from Huffington Post discovered it, and I hope at least he benefited from this discovery financially. But the point is that in this particular case, the robotic trader just never seen the Anne Hathaway in its training data, so every occurrence of the word Hathaway was attributed to Berkshire Hathaway. So what I want to do now is to give you 3 concrete examples when we have to tread very carefully when we are thinking about using neural networks. So the first lesson is deep neural networks today are extremely data hungry. And what I mean data hungry, I'm talking about supervised data hungry, when you know the answer when you're training your model, because this model have an input and they have an answer and they're trying to learn the mapping. So what you can see here is it's called CIFAR-10 dataset, for which deep learning model can do very well. It has 50,000 images. On it gets like 95%, which is close to human performance. However, if you cut your training set and only provide to the model 100 training examples, your accuracy goes down to 18.22, which is pretty much bad. And it's funny because sometimes I see people publishing paper and say, I trained my convolutional neural network on 100 images. So I can't quite imagine how did they do that. And there are, of course, various ways that you can go around it. First of all, you don't have to use deep neural networks. You can use linear models. Another powerful technique that came out is called data augmentation, because there are certain rotations of the data that don't change the label. For instance, in the case of images, you can just move the image around. It's still going to be a cat. And you can add this extra training data to help the model to learn. Another, very impactful way to do it is to do pre-training. Because think about it, what are we asking models to do? If we give to a model an image or a text, we force it to learn everything it could from this image and this label. So what we can do instead is to say, maybe we have some collections which are really large. In this case, it's ImageNet. It has 1.2 million images with labels, which have a cat and a dog and flower and whoever. And you train your model to predict all these different labels, okay? So what you are seeing here, for every single arc, you have a parameter. So there are like millions of parameters that you need to estimate, but it's okay because you have so many different images. Now, let's say we want to move to mammograms, and we don't have million-something mammograms annotated. We have much smaller set. So what you can do, you can actually reuse part of the models that you already trained. So you take maybe the first, n-1 layers from that model, and then only fine-tune the last layer on your mammograms. So in this way, you can actually benefit from all the simple shapes that you identify using the this big ImageNet, and then you only fine-tune it for mammograms, and it works really well. So let me show you another case, problem number 2, when we really need to be very careful with deep neural models. Deep neural models are not robust to distributional shift. So if you train your model to identify spam in your emails, it is not guaranteed to work on your Twitter, on something else. Like here you can see an example of system which was trained on image recognition. And you can see that if we train the model on black and white images, it's achieved performance of 99.4%, which is pretty good. Now, we're going to apply to the case where we're actually going to add some color here. And the target would have still the same digits, but with some color, you can see that the performance plummets to 52%. And this is actually really a crucial part, because whenever we are writing a paper, correct? We're writing a paper, we can take our training and tests that come from the same distribution. But in reality, whenever we are deploying system, the distribution changes. And even on my personal example, when we put the system for reading, these medical reports from Massachusetts General Hospital, we move them to another hospital, and the performance dropped, not by much, but it still dropped, even though they're part of the same healthcare system, just because they use slightly different language. And if the model hasn't seen exactly this language in training, it's hard to generalize. So let me give you an idea of what you can do that I'm sure you've heard about it. Is the technology is transfer learning. And let me give you an intuition of one way that may be working here. Let's say you have data in your training related to lipsticks, okay? And you try to predict whether the review about lipsticks is positive or negative. Is the task clear? It's standard sentiment classification task. And what you want to do, you want to take the system trained on lipstick and translate it into blenders, correct? You can say in general it should be working, because if somebody likes, says the word that they like lipstick, they should be maybe using the same positive words describing the blenders. The problem is that when you are going to be training a neural net, what you would discover most likely that the predictive word which would associate with a good lipstick would be best, favorite, which is good, but then the words like battery and pampa, which are not really applicable to blenders, correct? So the question is, how can I force my model to use the cues which would be kind of general across many domains rather than overfitting to the domain of lipsticks? And luckily enough, there is a principal way to do it, because what this neural model does, it takes a document and translates it into some multidimensional space. If we don't do anything special, it will translate the documents about lipsticks and about blenders into 2 different parts, because they would have different word distribution. But what you really want, you want them to be blended apart. And that's exactly what you do with an adversarial learning. You're kind of forcing the model to say, whenever you are making the translation, I want you to fail to identify where the translation of from the translation of the document, whether it is about lipstick or about blenders. So you're kind of forcing it to make this joint representation, and it happened to work very well and helps to translate the models across different domains. Let me now go to the third problem. And the third problem has to do with the fact that, first of all, we all know that the deep neural networks, they are actually black boxes. And if there is some bias in the data, they would land this bias in the data. So let me illustrate it to you on this particular example. So what do you see on the picture? It's not a tricky question, and the answer lunch doesn't go. Huh? Monkey, great. So what happens if you take this particular image and you remove the guitar? The trained model is going to correctly say that this is a monkey. However, whenever you're gonna add the guitar, and you don't do any special manipulation, you just add the guitar on top, how is it gonna recognize it? As a human. And the reason it happens, because in the training data, every single time when it saw guitar, it saw human, so it learns this correlation. There is nothing in the world that prevents monkeys from playing guitar, but the model is not aware of this fact, and it learns this bias. One way how we can deal with it. And sometimes, we are totally aware of the bias. We know there is some bias in the data, like, for instance, we want to represent different subpopulation. This is fine. But many times we may not be even aware that there is a bias in the model. And combined with the fact that the neural model had this reputation of having black box architectures, we're really in trouble. We may not even know what are the funny things that it may be doing. And we at MIT, my group worked very hard, and now there is a lot of work at Google and at Stanford and other places of how to make this model interpretable. And there are many ways how you can think about interpretability. So the specific example how we thought about interpretability is to say we're going to generate a rationale. Rationale is a part of the input which on its own justifies the label. So for instance, in this particular case, if you're looking at the text and want to know why this patient is high risk, maybe there is some particular phrase that makes the model think that the patient is high risk. Or if you're looking at the image, there will be some area of the image where the model looks and decides that this is causing it to make this prediction. So in this case, if we are making a prediction why the monkey is a human, the model would show to you that the guitar is the reason for making this decision. So at least it gives you an idea of what the model was looking at when it was making the prediction. And there are many different types of rationales that people are looking at, and this is still an open question. So just to give you an idea how these rationales are done, you're taking the deep neural network, which takes an input and output, and you break it in the middle. And you force it to say, select me some subset of image or of the text, which is a subset, which is coherent, and which on its own lets me to make the prediction. And you train this jointly, and you can see that it actually does pretty reasonable rationales. But for me, the question, and again, there is more work done every day in this area, so it's not really true to say today that these models are black boxes. But to me, the question that is of interest is, what happens when these machines, they already are better in predicting certain things, like example that I showed you with high risk, predicting who is going to get breast cancer in few years from now. Human eye cannot make this prediction, so even if machine visualizes you some complex pattern, you cannot understand the pattern. So, and as machines become better and better in this, and the patterns that they can identify would be much more sophisticated than what we can understand, the question is, what would it even mean to have, interpretable neural network? It can give you a rationale, but maybe we will be unable to validate the rationale. So let me just give few takeaway messages that deep neural networks are very powerful tools when they're trained on the right data. If you're going to take a package out of the box and apply it on small training data, when there is a distributional shift between training and testing, when they kind of have different properties, or when you have contaminated training, be it with bias, be it with whatever, we can find ourselves in trouble, and we should be really careful of moving forward. And in the remaining 1 minute and 46 seconds, I want to tell you about some new initiative that we've started at MIT, which I'm really excited. So we had a very generous donor who gave money to MIT to build a new initiative in machine learning and health. And the vision of this person was, his name is Mr. Jamil, that we can take all the great technologies that we're developing at MIT and not only give it to MGH and few selected hospitals in Boston area, but really change it and spread it across the country. And the barriers that, are well known for bringing AI to healthcare are issue of data access, regulatory issues, gaps in machine learning algorithms like the one that I presented, and also the lack of background in healthcare providers. So this initiative works in all the 4 areas. We work on technology development, we do large-scale clinical validation, we work on policy and education, and part of it supports entrepreneurship. And in the AI space, I already outlined you some algorithms that we are developing, how to reduce data needed for training, to make machine transfer better across population and increase transparency. One interesting technology that we are working on is how to make deep learning model learning in the private setting, where, let's say, somebody wants to give me their mammogram. Instead of giving me the raw image, they're going to encode it on side. My network would take this encoding, make the prediction, but I still cannot see it, and send it back, and then the person can open it up. So this whole question of how to access healthcare data and patient data is totally regenerated when deep learning works exactly on encoding and on the raw data. And this is an area that we're very actively pushing. And finally, we have a J-Clinic hospital network where we are trying this technology, getting feedback, and improving. And we hope right now we're primarily focused on the North America, but we hope as we move forward it's going to spread to other hospitals in the world. So with that, thank you very much.